All right, this lecture should be fairly quick if I can be efficient about it. Just going through free bodies when you have an object traveling around a curve. Um, the diagram is a little bit hard to follow, but this is a flat curve. Here's a car going around it. Its velocity is tangent to the curve, but horizontal. And here is the center of the curve. This arc is part of a circle. And to travel in a circle is necessarily to accelerate towards the center, and so there needs to be a force towards the center, and it is friction between the wheels and the track that would be specifically the road pushing on the car that would push the car towards the inside. But if you are doing the free body for this situation, you would have the um, looking at the car end on, you would have the weight pulling vertically downwards and the road pushing vertically upwards. And then in your free body, you would include the acceleration, which is towards the center of the curve. And then you would realize you needed a force causing that acceleration. And then you would scratch your head and come up with the fact that it was friction that was providing that force. And if you then go from this free body to sigma F is equal to ma horizontally in the direction of this acceleration, you'll just have one force, which would be equal to mu normal. And the normal, of course, you would get from sigma F equals ma vertically, and there would be no acceleration vertically. I'm not sure why the book stopped with flat, but it is much more interesting if this curve has a bank to it. Here is a 30-degree banked curve, and the thing is going around in a horizontal circle, and so the center of the circle is like this, and there needs to be a force towards the center, causing you to accelerate towards the center. But if we look at the forces that are here, you have the weight and the normal, which would be perpendicular to the surface, and the friction, which would be parallel to the surface. That there are no forces acting parallel to the acceleration until you break the vectors into components. And you can see that you have a component, and that's, I think, why it is so valuable to add acceleration to your free body. That you can see you need a force in that direction. Where is that force? There's a component of the friction that's that way and a component of the normal that is that way. And knowing this angle here, 30 degrees, you could figure out this angle here, and from that angle, this angle, and that angle, and then you could get those components. You would want to, again, break it into the two sigma f's, and there is no acceleration vertically and acceleration horizontally. Now, here's, I had an acceleration all set to go. Boom, there we go. That's not the only way to do it. I think it is the most reasonable way to break your vectors, all the vectors going parallel to this acceleration and all the vectors going perpendicular to that acceleration. But it is also possible to do the same problem and deal with all the vectors going parallel to the track, in which case you would have a component of the weight and all the vectors going perpendicular to the track, again a component of the weight and the normal. But if you did your sigma f's in those two directions, you would need to, when you wrote sigma f, write sigma f. Sigma f equals ma. Here, let's go with the ones that are going parallel to the track. You would have the friction going parallel to the track, and in the same direction you would have the component of the weight. If that's theta, then that's theta, so that's W sine theta. Is equal to, and here you would have MA, and it would not be all of A, it would be this component. And let's see, boom, boom, that angle there is 30. So it would be A cos 30. I can't squeeze that in. And then similarly, perpendicular, you would have these two forces. One of them would be a component of the weight, but then you would have A sine 30. It would be what it was equal to. So I think that's a little bit more cumbersome, but it could be done. Just be very careful to not cut any corners and leave things out. Finally, we're going to look at this problem about Allo Daredevil Diavolo, who evidently in 1901 debuted this trick of riding around a loop-to-loop. And the problem, it's a classic problem, and you need to feel good about it, is to find the minimum speed that Diavolo must have at the top of the loop. And later on, we will do a problem with how high he must start up the ramp in order to have that speed when he gets to the top of the loop. That's an energy problem, because the acceleration is not going to be constant throughout that trip. So you have to do it in terms of energy. But the minimum speed requires an understanding, which if you don't already have, you will gain now, and it will be invaluable to you to hang on to that as you do these problems. Here is Diavolo at the top of the loop-the-loop, and the forces acting on Diavolo are going to be weight, and at the top of the loop, the normal force from this track he's riding on will be pushing him inward as well. And if you do your sigma F equals MA, I have that. Okay, we're going to write it. Soon we're going to write it. Sigma F equals MA, and we're going to do this vertically, because the acceleration, after all, is towards the center of the circle. So it's a lovely agreement here, and what you have is the weight plus the normal is causing this mass to accelerate towards the center. But of course, the acceleration is going to be centripetal acceleration, so it's going to be v squared over r. It's going to be that acceleration. But this minimum speed issue here, you need to realize that as Diavolo goes slower and slower across the top, as this velocity gets smaller and smaller at the top, the centripetal acceleration is going to get smaller and smaller, which means this side of the equation must get smaller. The weight can't get smaller. That's completely determined by Diavolo's mass and the acceleration due to gravity. And so the normal force, as Diavolo goes slower and slower across the top, this vector will shrink until at the minimum this vector will have become 0. And the equation you'll be dealing with, instead of w plus n, will be just w as you go across the top. Now, if you go any slower than the minimum, this value here will get smaller still, but the weight will not be able to get smaller to match it, and so there will be too much force here, and the acceleration that you have will be too big. That is, you will accelerate towards the center faster than the rate that leads to circular motion, and what Diavolo will do would be to tend to fall into the circle. He will leave the track in that case. So this is the equation that arises for minimum speed across the top of the loop. And you can see, and you will do this on your worksheet, you will find that value of V, the minimum speed that you should have to go around the top of the loop. And then when you do that, hang on to it, because it will be a useful trick for you to be able to pull out of your bag of tricks later on. Thank you.